Sometimes you can't just plug that in. Check out this example 6. What if I have, here's A. This was other techniques. The limit as x approaches 2 of x squared minus 6x plus 8 over x squared minus 4. What happens when I just plug this 2 in? That's still my go-to method. But look at what happens. I have 2 squared minus 6 times 2 plus 8 over 2 squared minus 4. Yep. Do you see that? 4 plus 8 in the top, that's what I did in my head. 4 plus 8 is 12, minus 12 is 0, and then 4 minus 4 is 0. Okay, if you come up with this 0 in the denominator, if the 0 in the top, nobody cares, but the 0 in the denominator, I can't do something like that, right? That's what our law said. You can't have a 0 in the denominator. So if I can't have this 0 in the denominator, and we have these polynomials, factor. Oh, factor. Oh, man. Isn't that good stuff? Man, I bet you thought, man, when am I ever going to use factoring again? Right now, guys, right now. You get to use factoring right now. Notice, I plugged it in here, so I dropped the limit notation. But I am just manipulating this part of it, so you have to keep your limit notation. Until you plug it in, keep that limit notation. So what do we have here? X minus 4, x minus 2 in the numerator, right? And x plus 2, x minus 2, because it's a difference of squares. Check us out. Simplify that rational expression. Remember, a limit is what is my graph approaching. It doesn't have to be the value. Right? What is my graph approaching? Even though I have this hole in, oops, I meant to hit this. Even though I have this hole in my graph right here, that's okay. I can have a hole and still have a limit. So I'm really finding the limit as x approaches 2 of x minus 4 over x plus 2. Now when I plug that in, I get that negative 1/2, right? Because negative 2 over 4 is that negative 1/2. Okay, you can still have a limit, an actual limit of something. Whenever I'm looking at this, whenever you have that hole in there. So I can still look at that. So here's what the graph looks like. Add a photo from my camera. Oops. Let me scoot this over. You see that? There's my hole in the graph. But I still have my limit as I approach from the left and I approach from the right so that I can have that. Here it is at that negative 1/2. And we know that to be the case. All right. Whenever you factor it out, this is your actual graph. But here, if I'm approaching from the left and from the right, it's okay to have that hole. I still have a limit of my function. And that's the kicker. Good. All right. So if you have a rational expression, you can factor. If it looks like it has a bunch of polynomials in there, you can factor. Look at this. What if I have the limit as x approaches 1 of the square root of x minus 1 over x minus 1? Plug it in, and we have an issue, right? Okay. So if you can factor, that is one technique. So we ought to write that over here. So one technique here is to factor. Another technique is to rationalize. Rationalize. All right? If you rationalize, remember that? Kicking it real back here to algebra, right? If you rationalize, then I'm looking at this. Let me scoot this up. Typically, whenever you would rationalize the denominator. I always talk to my pre-calc students, and I'm like, yes, typically we rationalize the denominator to get that radical out of the denominator, but as you go forward, you're not always going to rationalize the denominator. Just like in this one, I'm not going to rationalize the denominator because my issue is the numerator. That's where my radical is. So I have not taken my limit yet, so I'm going to keep writing it. Until you plug it in, you rewrite that limit notation because I haven't performed that operation. So we're going to rationalize the numerator. Do you remember how to do that? Yeah, good. It's like the difference of squares. You take the exact same thing. One's a plus and one's a minus. Whatever you do to the top, you have to do to the bottom. Right? And then you multiply it out. Because this is the difference of squares, square the first term minus square the second term, right? Get back to blue. So I have my limit as x approaches 1 here of, if I square the first term, that gives me an x minus square the second term. Now I did this top first. Do you see what just happened? Maybe? Don't multiply this out. Leave it exactly how it is, because look what we just did. You now have those in common, and plugging this 1 in was the issue, and that's what gave me that 0 in the denominator, right? Now that I have canceled that out, I can actually take my limit. Scoot this up a little. Of 1 over the square root of x plus 1, right? No, oops, that looks like it's a little crazy there. Let me clean it up a little. My poor handwriting. Sorry, guys. I got a whole semester of it. You have to keep this 1 on top because this square root of x plus 1 is still in the denominator. Just because it's canceled out, it doesn't go away. You divide both of these and you technically get a 1 over 1 here. 1 times anything is itself, but you have to keep that 1 on top. That's a common algebra thing that people mess with. Then I plug it in. Once you plug it in, you drop the limit notation. The square root of 1 is 1, so I get that 1/2. All right? So if, let's squeeze this back in, very first go-to method, plug it in. If you plug this in and you come up with an issue and you've got polynomials, factor it. If you plug this in and you come up with an issue and you have a radical, rationalize. All right? We are going to, as this semester progresses, learn more ways in order to work with limits, but here's our basics. Step 1, plug it in. Step 2, if you can factor, do it. If you can rationalize, do it, right? Only if you have an issue. The only time you ever have to do that is if you have an issue. You could have radicals all day long and it's no problem, right? Look at this one. We had a bunch of radicals, but I was able to plug it in, so we're good.